All right. Well, my name is Nick Estes. I'm the Science Operations Center Manager for the Lunar Reconnaissance Orbiter Camera and the Shadow Cam instruments that are operated here at Arizona State University. And we're going to talk a little bit today about the data processing that we do. We do a lot of data processing supporting these lunar missions. But first, we'll take just sort of a brief look at the moon of the type of exploration we're doing, the cameras we're using to do it, and then we'll take a deep dive into all the data that comes out of these missions. So as you can guess by the names, we are looking at the moon. The moon's lunar day is 28 Earth days. It's tidally locked, so it rotates at the same speed that it orbits. Because of that, we only see the lunar near side. In this picture here, we can see the far side, and it's actually quite dramatically different. The gravity of the moon is only 1/6 that of Earth, and it's about 250,000 miles away. What's kind of interesting for exploration is the moon's axis is only tilted about 1.5 degrees, which means any craters near the poles never get any direct sunlight. So if you're operating a spacecraft orbiting at high altitudes, imaging in the dark is quite a challenge. And so that's where the second camera, Shadow Cam, comes in, is to help us fill some of those gaps. We believe the formation of the moon may have resulted in the larger axial tilt of the Earth of 23.5 degrees, and the moon helps to stabilize that tilt. And because of that, the stabilized tilt and the tidal action of the moon, it actually provides a lot of the conditions that make the Earth able to support life. So aside from being really interesting for exploration, it's also very important just for us to be here. Some basics of the moon. When you look up and see the moon at night, you see a lot of these dark patches on the near side that we don't have on the far side. And so those are Mare basalt. So those are large ancient impact basins that filled with volcanic activity. And so that lava rock, that basalt, is what makes all those darker areas. The bright areas are anorthosite, which is ancient crust formed for a magma ocean a little over 4 billion years ago. So some of the value of lunar exploration is it's a well-preserved record of early stages of planet formation. There are no plate tectonics, there's no atmosphere, there's no erosion. And so it has a well-preserved record going back billions of years of what's happened in this part of the solar system. And the things that have been happening to the Earth in all this time have also been happening to the moon. So it can tell us a lot about solar system formation. It can tell us a lot about what has happened on the Earth through preserved evidence of impacts over a very long period of time. It can also be a really good test bed for engineering. If you're experimenting with habitats and other technology for space exploration, it's much better if you're only 3 days from Earth if something goes wrong rather than months away. So to do all this lunar exploration, the first instrument that we operate here is the Lunar Reconnaissance Orbiter Camera. It went up on the Lunar Reconnaissance Orbiter, and it's one of 7 instruments on board. And so we're the only camera system, but the other systems involve thermal detection, laser altimeter, there's a radar instrument on board, and others as well. The spacecraft was built by NASA's Goddard Space Flight Center, and it was part of future human return to the moon that started back in 2004. After that, focus kind of changed away from the moon a little bit, but now with the Artemis mission and other exploration efforts, it's coming back to the moon. So we've kind of come full circle back to our original mission of helping to support manned exploration to the moon. So the Lunar Reconnaissance Orbiter launched on an Atlas V rocket on June 18th, 2009. It took us only about 5 days to get to the moon. It had a pretty direct trajectory. And so we've been operating at the moon now for slightly more than 14 years. So the LROC instrument is actually made up of 3 cameras. One of these cameras is the wide-angle camera. And so this has a short focal length. It's about a 90-degree field of view in the visible range, 60-degree in the ultraviolet. And it has 7 bands. So 5 of them are in the visual range and 2 of them are in the ultraviolet. At our primary mission orbit of 50 kilometers altitude, we had a resolution of about 100 meters per pixel. Right now, our altitude's about twice that, and so our resolution currently is around 200 meters per pixel. But with this camera, because it has such a wide field of view, we can actually get global coverage over 28 days. And so all that repeat coverage over more than 14 years of data collection actually allows us to build up a pretty comprehensive data set at multiple lighting conditions. And this allows us to make 3D models and photometric models and a lot of other science capabilities. The other two cameras are a pair of these narrow angle cameras. We call them the left and the right. It has a much smaller focal length. The field of view is 2.86 degrees. And with the two side by side, they overlap just a little bit in the middle. It gave us a width at our primary mission orbit of about 5 kilometers. It had a resolution in that orbit of 0.5 meter per pixel. And just like the WAC, that goes up as we go up into our current orbit of closer to 100 kilometers. So we're around 1 meter per pixel right now. So the third instrument we operate just went up last year on the Korea Pathfinder Lunar Orbiter. So this was built by the Korea Aerospace Research Institute as the start of their lunar program. Korea had never launched any satellite outside of the Earth's orbit before. And so this is kind of their exploration effort to do some mapping of the moon before they send additional missions in the future that'll include landers and rovers and that sort of thing. We are one of 6 instrument packages on board the spacecraft. One of them is the Lunar Terrain Imager, which is a similar camera to the NAC, a little bit lower resolution. They have a polarimetric camera, a magnetometer, gamma ray spectrometer, a networking experiment, and then shadow cam. So as Korea was putting the satellite together, they approached NASA and said they had a little bit of mass and a little bit of power available and asked if NASA would like to participate in this mission. So a request for proposals went out and we proposed shadow cam. And so as I mentioned towards the beginning, the moon has just that 1.4 or 1.5 degree tilt on its axis. And because that tilt is so small, the angle of repose of a crater on the moon is about 30 degrees. So that's the angle that the wall will be at after all of the debris kind of settles. And so you can have craters as low as around 70 degrees latitude that never get direct sunlight in parts of them. And so all the current exploration efforts, such as the Artemis missions, some of the Eclipse missions recently been making the news, and other volatile materials available as resources on the moon. Those are the locations where they're most likely to be. So a little more details about shadow cam. You see in this picture, it looks very similar to the narrow angle camera, and that's because it's based on it. It's actually the same telescope design, except it has a lot more baffles inside of the metering structure here, and that's to keep stray light out. So because the goal of shadow cam is to image in these areas that never get direct sunlight, it has to be a very, very sensitive instrument. And so any amount of stray light that gets into the aperture of the telescope can really wash out the entire scene. And so that was one of the most significant changes, was just keeping as much of that stray light out as possible. The other big change is the sensor itself. It's a type of sensor called a time delay integration sensor. And in this particular case, we have 32 stages. And the way it works is as the sensor is moving over the surface, the signal transfers from one stage to the next, and that effectively boosts the signal. And so between that and a little bit larger pixel scale, we're able to have almost 200 times the sensitivity of the narrow angle camera, which is enough to see in these permanently shadowed regions. Shadow cam is at roughly 100-kilometer orbit. And at this orbit, our pixel scale is about 1.7 meters per pixel. So it's still pretty high resolution, and certainly the highest resolution images that have been taken in these permanently shadowed regions by any instrument. So some of the images that we've taken, this is what we call our first light, the first image that we took with LROC when we got to the moon. And this is actually right at the South Pole. This was taken on June 30th, 2009. And this map projected pair shows the crater, the rim of the Shackleton crater. And the South Pole is right off the rim of Shackleton crater. So we're almost directly at the South Pole here. And then what was kind of exciting, when ShadowCam got into orbit after a 5-month cruise, it took a little bit longer cruise than LRO did. We looked at the orbit tracks, and we were actually passing directly over the same area that we had LROC's first light in. It was a few days before the mission was supposed to start, but we made a request to our colleagues at the Korea Aerospace Research Institute and asked if they'd allow us to take an image before they had quite finished all the checkouts. And they were able to accommodate us. And so in this case, we're seeing the interior of the crater. The interior of this crater normally sees no illumination at all. And so this is just using reflected light. If we look back at the LROC image, we can see with LROC, we get the outside of the crater, and then with ShadowCam, we get the inside. And we'll take a closer look at that before we dig into the data. So some of the other images that we've gotten that are interested, we've been able to image all of the Apollo landing sites, and the narrow angle camera is high enough resolution. You can actually see in this image, depending on how good the projector is, you can see some of these trails of where the astronauts actually walked on the surface. And, because no water, wind, erosion, or anything like that, those trails are still preserved after 50 years. We were able back in 2011, 2012 to actually lower the orbit of LRO over the Apollo landing sites from our nominal 50 kilometers down to almost 20 kilometers. And so we can see here, this is the descent stage from Apollo 11 on the right. And there's a picture on the left of the Apollo 16 descent stage as filmed from the LRV camera. And, at that lower orbit, we were able to actually get quite good images on the surface to really see the details in this hardware, but also the details in the surface itself. There's, of course, a lot of impact cratering. That's what you think of the most when you think of what's on the moon, is a lot of craters. This particular crater is Tycho. If you look up the full moon in the southern hemisphere of the moon, there's a very small, very bright crater with a lot of rays coming out. That's Tycho crater. It's about 82 kilometers in diameter. And we can actually take a closer look at the central peak here. And if you look on the central peak, you can see this boulder right here sitting on top. Just to give you a sense of scale, that boulder is roughly the same size as the Sun Devil Stadium at the university. So it's very big features here and a very big boulder on top. Now, I mentioned that the moon has no plate tectonics, but we do see tectonism on the moon. It's because originally it had a liquid core, and as it cooled over a long period of time, the moon shrinks. And so the solid crust has to go somewhere, and it creates tectonic features. And we have found hundreds of these small faults all over the moon. We've also seen what we think are signs of recent volcanism. That's recent in geologic terms, not in human terms. But here's a picture of Ina D, which we believe is a volcanic type of feature, but there's a lot we don't know about it. And that's some of the great parts of lunar exploration, is it's not all about finding the answers. A lot of it's about finding the questions. We've also seen a lot of these pits. There's originally just speculation about these pits. On an earlier Japanese mission, the Kaiguya spacecraft, the Selene instrument found 3 of these pits. Since we've been in orbit, we've found hundreds of them. This slide is actually slightly out of date. We're closer to 400 or 500 of these pits that we found. What we believe they are is like a collapsed skylight into a lava tube. So if you've ever had the opportunity to go up to Flagstaff and explore the lava tube that's up there, it can give you some idea of the type of feature we think we're seeing here. And this can be really great for a variety of reasons. One, you can see in this image on the lower left, you can see the layering of all this volcanic material that got deposited. So being able to study the history and see how the chemistry of the material changed as these were being deposited can really tell us a lot about the moon's formation. This can also tell us a lot about the Earth, as I said, because they're neighbors and they've been subject to all the same features. The other useful feature for these lava tubes is if it does go back under the surface, it's potentially a place where you can use them for habitats. One of the challenges of putting humans on the moon is protecting them from solar flares and radiation in general. It only takes about a meter thick of the moon's regolith to completely protect astronauts. And so if there's room to put a habitat in a place like that, you can get all of that radiation protection essentially for free. So aside from just straight images, there's a lot we can do combining images together, such as making 3D models, or in this case, an illumination map. So here we're looking at Shackleton Crater again, where the South Pole is right here on the rim of Shackleton Crater. And what this is showing is the percentage of illumination that this area gets. And so again, going back to that 1.5 degree tilt, it results in these areas that receive no illumination at all. So all these black areas are 0% illumination. But that same tilt also results in peaks that get a lot of illumination. Some of these brightest areas here are somewhere around 90% illuminated. So this can be really exciting for exploration. If you're powered by solar power, being illuminated 90% of the time is a great benefit rather than only 2 weeks light, 2 weeks dark as you get near the equator. And having that sort of power source for whatever lunar habitat or station you set up next to these permanently shadowed regions, which are the focus of all this exploration, are really great locations to go to. So you may have seen recently, and it was published in National Geographic. It was also featured on Good Morning America, Space.com, and a few other sites. There was some of the first imagery of shadow cam shared. So this right here is an LROC image, a narrow angle camera of, again, Shackleton Crater, the same area of the South Pole we were just looking at. And so now with shadow cam, we can start to fill in these shadows. We can start to see what's in the dark and really put the story together. There's been lots of instruments that have detected various forms of hydrogen or ice or other signals like that in these permanently shadowed regions. But finally having this visual data set to help us see what's actually there and tie these together, I think is going to be really helpful for lunar exploration. But of course, to do all of this science and all this exploration, it results in a lot of data, and the data is what we're all about here at the data conference. So the data collected by both the LROC and ShadowCam missions is relayed from their Mission Operations Center, which is Goddard for LROC, and the MOC at the Korean Aerospace Research Institute for ShadowCam, and is transmitted here to ASU. And this raw data set is processed into a variety of standard forms and then further processed into assortment of useful science products. And all of this processing is happening on campus at ASU data centers, and the public data set is archived and served to the world from here as well. The types of data products we're looking at, the primary product is our EDR, the experiment data record. This is the closest form to raw camera data that we archive. The original data from the spacecraft is decompressed, and all of the metadata necessary for further processing and understanding this data is added to a product label, and that's the EDR. It's an 8-bit product. From there, the data gets calibrated, and for LROC, this becomes a 16-bit product. For ShadowCam, this becomes a 32-bit product. And what these calibrated data records do is they decompand the raw data from EDR. If you're not familiar with companding, it's like a linear transfer method. The cameras themselves are 12-bit for both instruments, and they use companding to go into an 8-bit space, but it's kind of an adjustable curve that allows you to focus on the areas where you need the most clarity of image, and then kind of cut out some of the data where you need a little bit less. So we decompand that, and then we put it through our calibration pipeline, which includes dark subtraction, gain correction, and radiometrically correcting the data. And then that gets archived as a CDR product. And then we've got a team of folks that make reduced data records. These can be either 8-bit or 32-bit. And the RDR term kind of covers any product that is non-reversible, derived from the raw or calibrated data. And this can include 3D models, controlled mosaics, illumination maps, shape files, just sort of anything you can imagine kind of falls under that umbrella. There's also a lot of ancillary products we make. And so each of these primary data products comes with a set of ancillary products that can include histograms, browse images, pyramidal TIFFs, legends in the case of color maps, and things of that nature. So processing and storage. Our processing is managed by a software package called Rector that was written by the LROC SOC. Our processing cluster itself has 17 nodes that has more than 800 CPU cores in it at this time. All of the image metadata, our file catalog, target information, everything else is stored in a Postgres database. And our file storage is on an Isilon storage system, which currently sits between both our primary and secondary together at about 10.5 petabytes in size. So the Isilon primary syncs to the secondary once an hour, and 20 days of these snapshots are retained. So if anything goes off the rails, we've got time to identify it, restore to a good state, and continue. There's also an additional backup to external drives of only the source data, not the process data, because for the planetary data system, we are required to have 3 copies of all the data. Because our data is so large, that source data counts as our 3rd copy. So our primary data center is right on the ASU Tempe campus, and our secondary data center we use is at ASU's Poly campus out in Mesa. So it's kind of an overview of the network. We've got 3 buildings that we primarily deal with. So right next door in Interdisciplinary A is where our main offices are. And so there we have our office systems and a connection to our research network. ISTB1 is where the primary data center is. And so that has our PDS node systems, web servers, our data exchange systems, half of our processing nodes, and our primary database and primary storage. Out on the Poly campus, we have kind of the second half of those processing nodes and storage and database, along with some backup servers and a central logging cluster. Most of this goes normally through the ASU security complex like everything else, with the exception of PDS. PDS, because it's effectively a large random data set, and so it regularly trips false positives on any of the application detections that were going on. And so that had to be bypassed because it was preventing our data from being downloaded. So we've got special security on there that locks it down to a read-only data set. And so that only goes through the effective parts of the ASU security complex. But that PDS data node is also capable of going out that route over a 40 gigabit connection to both the internet and Internet 2 users. So we mentioned Rector, our job management system developed here at the SOC. This is split between doing a few different types of jobs. It can be well-defined nominal processing tasks. Those are the ones used to create our key data products that go to the planetary data system. And it can also be used to make ad hoc user jobs to run any task across the processing cluster. The science team uses this to, for example, map project products and do various types of. It's also used by our outreach team. Some of our 3D animations that are available on our website are creating a software package called Blender, and we can also run that across the processing cluster to help speed up the rendering of those videos. So Rector allocates jobs to servers based on CPUs required and the expected memory footprint of each job. And it balances prioritized jobs to ensure that mission-critical processing occurs first and with minimal delay. And it also ensures that all users waiting to run jobs get some portion of the cluster, despite what order they may have gone in the queue in current load conditions. It's not unusual for one of our researchers to queue up 100,000 jobs or more for a certain type of processing. And then if somebody else comes in and only has 10 jobs that they need to run, we don't want them to have to wait a month for their 10 jobs to pick up. And so it balances between job submitters as well. In aggregate, more than 17 million CPU hours of tasks have been managed on the SOC's processing cluster with Rector. For the LROC project, that's been 107 million jobs using 6.5 million CPU hours. ShadowCam, which we're still not quite to the end of our primary mission, that'll be in December. We've already processed 3 million jobs using 39,000 CPU hours. We also host at our facility the Apollo Digital Flight Film Archive. This is an archive of all the original Apollo products scanned from the source film. It is the highest resolution available of any of the Apollo products available anywhere. And that was also processed on this cluster using 310,000 jobs and 60,000 CPU hours. And then those ad hoc user jobs are really where a lot of our science work happens. And so this is used more CPU hours than anything at 10.6 million CPU hours doing all of this customized work for the science team. So our database is hosted on a pair of Postgres database servers. Both of these servers have 256 gig of RAM and 32 cores. The database itself isn't too huge compared to the data. It's only 3.4 terabytes on Gen 4 SSDs. It uses Postgres built-in replication to make the secondary act as a hot standby. And this enables us to do read-only operations on that backup server in cases where it's going to overload the primary too much. So it's not just backup, but also gives us more query capacity. That secondary lags in data duplication by only a few milliseconds. And generally, this results in no data loss, even in the event of a total failure of the primary, which has only happened once in the just over 14 years of the mission. There was a hardware failure about 10 years ago that basically took out the entire database file system with it. But because we're using the built-in replication and everything, we had no data loss, which was fantastic. We also use the point-in-time recovery in Postgres, which means if something were to go awry but not necessarily take the database offline, we can recover the database state to any time covered by the backups. And it's a 4-week window that we keep online for that. In terms of overall database performance, this is from October data. We process around 4.8 million queries a month. The primary database server serves about 87 days of processing time in that month. So it's roughly has 3 CPUs active all the time on average. We also have loaded into Postgres an extension called PostGIS. And so this basically gives a lot of geographic information system features to Postgres. And we added to that new spatial reference system data, which allows PostGIS to support moon data and native planetary projections. So as you can imagine, with all the moon maps and other data we have, it's really nice to be able to have these GIS features directly into the database. It also has software available that easily converts between standard GIS formats, such as shapefiles, GeoJSON, and other things, and the PostGIS fields in the database. So it's easy to go back and forth without anything complicated going on. So our storage system, as I said, is based on Isilon. We're actually in the middle of an upgrade right now, which will hopefully be done in a couple of months. This is what the cluster will look like when the upgrade is finished. The primary storage system will be at 5.76 petabytes in raw drive space, which equates to about 5.12 petabytes usable. And the secondary is about 4.8 petabytes raw space, which equates to about 4.27 petabytes usable. So the aggregate raw storage, as I mentioned, is around 10.5 petabytes. At this scale, though, it is really important to note your unit. So these are all base 10 petabytes. The same number in base 2 petabytes is only 9.38. So as you're working on storage expansion or estimating the size of new projects, things like that, at this scale, it can be a quite significant difference between those units. So you have to be very careful to make sure you're using the right ones. So as I mentioned, all of our data goes out to the NASA Planetary Data System. The PDS is operated by 6 discipline nodes that kind of divide the work of archiving different types of planetary data collecting by NASA instrument teams. And so the LROC data is archived with the imaging and cartography discipline node. Because the LROC data is so large, it actually makes up more than 65% of all of NASA PDS is our data. And because of that size, we're not stored directly at the discipline node. We're actually stored and served from a dedicated data node. And that data node is in the ISTB1 data center served here at ASU. So it's kind of a really cool fun fact that, by volume, a large amount of the NASA planetary data system is actually on campus served by systems here at ASU. Our Isilon storage system that we looked at holds both unpublished and published data, but because it's implemented as a flat file system, the large data deliveries can happen very fast because it's only a metadata operation, not an actual file transfer. And that's the big benefit of hosting it on campus, is because that publishing can happen so quickly. So all of the LROC EDR, CDR, and RDR data is archived in PDS on the local data node. Each EDR and CDR is released with a full resolution, lossy compressed pyramidal TIFF browse product and a histogram. And each RDR product is released with a GeoTIFF, another pyramidal TIFF browse product, and a README with more details on the product. Our release frequency increased from quarterly to monthly, starting with volume 36A back in October 2018. So these days we're on a monthly cadence of data releasing. Our next data release is actually going to be early next week. The pyramidal TIFFs that I've mentioned is something that's used by both the LROC and ShadowCam missions. And so all of our products are available in this pyramidal TIFF format, in addition to the PDS archive formats. And the great advantage of this is that this format facilitates the browsing of the full resolution of the entire data set in all processed forms within your web browser without downloading any data products or any special tools first. This format was not widely used when LROC first started, but the utility of this has really become apparent on a wide variety of applications, and it's since been standardized as the cloud-optimized GeoTIFF format. All of the pyramidal TIFFs generated for the ShadowCam mission are compatible with the cloud-optimized GeoTIFF format. The LROC pyramidal TIFFs, there are some small technical differences between the COG standard and what we've been making for 14 years. And so these are slated to be reprocessed into COG-compatible products within the next year. So the current size of our planetary data system release, as of our October release, is about 1.5 petabytes total. This includes EDRs, CDRs, RDRs, and all those ancillary products. There's just over 59 million files altogether in our PDS release. The first ShadowCam PDS release won't be until early 2024, so stay tuned for some exciting data coming from that instrument as well. In terms of use of data by the entire world looking at moon exploration, as I said, it all comes from our LROC data node hosted here at ASU. Over time, we were getting somewhere around 2 million hits a month in traffic, with a few exceptions here and there when large transfers were attempted by the PDS nodes. But as we can see, in 2021, we actually started seeing some huge increases in traffic. And this actually started about halfway through 2020. We can see in May, we had 3.5 million hits. And then suddenly in June, we were at 15 million, and then 25 million, and then 43 million. At the point where we hit 43 million hits in the month, it was overloading our current web infrastructure. And so at that time, we actually split off our PDS data node as its own dedicated service. That's when we worked with research computing and enterprise technology to get that dedicated 40 gig uplink from the PDS nodes, and we ended up putting them on dedicated servers. And so with all those changes together, we can see in March 2021, we peaked at 1.6 billion hits in that month. It's just a huge amount of data transfer going through. After that time, we've never quite returned to normal. In fact, last year we had another peak at 1.2 billion hits in a month. Although this year we've been pretty steady, close to 5 million hits a month, most months. Kind of a fun fact, in the years from 2012 to 2019, we averaged 33.8 million hits per year. And that peak in 2021, we hit 44 million hits per day. And so we were doing, a third more traffic every day than we were doing per year before this peak happened. So in terms of data distribution, primary distribution is through that PDS data node, through NASA PDS. We also have our own PDS search page that allows some customized searches that aren't available through the NASA system. Since the NASA system has to support all missions, ours can be a little more customized to our missions. We also have Quick Map available, which is kind of a in-browser GIS tool. It allows us to bring a lot of lunar data sets together and do a lot of analysis without needing specialized software like ArcMap or QGIS or something like that. If you are doing analysis in a GIS system like ArcMap or GIS, we also have Luniserve available, which is something we wrote in-house in the SOC to support the WMS protocol. It's an open standard web map service protocol, and all of our data is available through Luniserve. So any of these standard GIS tools that can talk to WMS can also plug into our data set that way. We have a lot of featured sites available where we've taken curated images of places that people are particularly interested in. So these are things like the Apollo sites, some of the modern impacts, some of the new missions that have arrived at the moon. These are available in our featured sites. And we've also taken a lot of that and put it together in a standalone kiosk that can operate without the internet. We have one of these available that you can play with in our SOC here in Tempe, Arizona. There's also one at the National Air and Space Museum in Washington, D.C. There's one at the Reese Crater Museum in Germany. And there's also one on a traveling New Moon Rises exhibit. We also put together a navigating LROC data brochure because there's so many different types of data and so many ways to get it. We thought it was helpful to kind of lay everything out in one place so you can kind of pick and choose what you're trying to do with LROC data, and it'll help you find out the best way of getting to that data. We're doing a lot of support for other lunar missions. There's over 300 images that we've taken specifically in support of the Commercial Lunar Payload Service program, and many more that were not specifically taken for CLIPS that have proven useful to those same companies. We've made 44 digital terrain models for these landing sites. We've taken more than 2,000 images in support of international landed missions, such as the recent Chandrayaan-3. And we've also created digital terrain models to support those as well. So some of those fun RDR products that we've mentioned, they come in a lot of forms. We've got a lot of global maps, such as our WAC global morphology map, photometrically normalized maps, and a bunch of other WAC mosaics. We also make controlled mosaics, digital terrain models. Many of our digital terrain models are either 2 meters per pixel or 5 meters per pixel with very high accuracy. It's all tied to the laser altimeter data. Made photometric series that can help understand the composition of the surface, polar mosaics, NAC anaglyphs, a lot of change detection. That was actually the focus of Emerson Speyer's PhD that he just got this year, and a North Pole gigapan, which is a 2 meter per pixel image that extends from 60 degrees latitude to the North Pole. It is an absolutely huge product and pretty fantastic to look at because you can zoom way into the details. And there's a lot more. So in terms of coverage, after a little more than 14 years, a question we get a lot is how much of the moon have we actually taken a picture of? Which is a very difficult question because it all comes down to lighting conditions. Just because you've taken one image at a place doesn't mean you've learned all that you can learn or all that you need to learn using just images. And so this is kind of a table separating out based on lighting condition and latitude range. And you can see under some conditions, we've actually imaged almost entirely of the moon's surface. But in other conditions, we only have 64% coverage in the case of an incidence less than 45 from pole to pole. So it really depends on the kind of science that you're trying to do, but we're going to continue taking these images and filling in these gaps as long as the spacecraft continues operating. And so how much data is 14 plus years of data? It's 14.3 trillion pixels of WAC data and 425.3 trillion pixels in ACK data. This is enough pixels total to print a square mile at 330 dpi, so still high enough resolution where you need a magnifying glass to see the dots. We have a couple of fun visualizations. We'll see if one of them will pop up here. So this was a visualization that we made for our 10th year anniversary. And these dark bands you see across that are actually showing our beta cycle. Every 6 months is what it takes for us to transition from dawn to dusk, basically, on the lunar surface. But if we zoom into this image, this is actually made up of a center crop from all of our NACs that were taken at our 10-year anniversary. So this is a fun product you can find on our website. You can really do a lot of exploration, kind of see what we've seen with the NAC through the years. So kind of some conclusions. We've got ongoing temporal imaging, geostereo observations, NAC coverage filling, and other opportunities that continue to expand and improve our knowledge of the moon. All of the renewed interest in lunar exploration with NASA's Artemis mission, the CLIPS program, various international efforts are also leveraging this LROC data here at ASU for mapping and planning purposes. And this includes acquiring new stereo and other targeted observations in direct support of these missions. Managing this data set and making it easily accessible have been challenging. It's quite a large, extensive data set that we have here. But automation and a variety of tools giving fast and accurate access to the data set provide a means for the lunar science community to make the best use of this extensive data set. And we're very fortunate to be able to work on these missions, and we're excited to support these missions here on the ASU campus. And so, unfortunately, I couldn't be there in person today, but our SOC facility is right next door to the Memorial Union in Interdisciplinary A. And I know after the session or breaking for lunch, person from my office, Megan Hendrickson, she is on her way to the MU right now. She should be there momentarily. And if anyone is interested in a quick tour to see our operations center, we also have an actual moon rock collected by the Apollo 15 mission on display there. You can come with Megan and she will give you a tour. We also have postcards, posters, and maps and other materials available. And so that's all I had. Does anyone have any questions for me? Well, it looks like we're having an audio problem from the room. I cannot hear you guys.
Nick, can you hear us?
Yes, I can hear you now.
Okay, hold on.
Hey, Nick. Okay. The sense of scale that you're dealing with is so different than what we typically do here at ASU. Most people are working with thousands of records, sometimes millions. On the occasion, we're doing billions, and just can't even fathom the amount of data that you're processing. So I've been to the operations center before. It is incredibly impressive. I've also been through the server rooms back when Chris Kurtz was out there. And I was a little surprised to see that you guys are still very much on-prem. And I'm wondering if just the scale that you're working in and the types of read-write operations, you mentioned speed of publishing, does the cloud not work for that type of environment?
No, not really. It's something we've looked at. In fact, years ago when the ASU supercomputer Saguaro, the first one on campus, was active, we actually tried using it because it had, we have a lot of processing power in our own cluster, but Saguaro was vastly more powerful than what we had in our cluster at the time. And we were able to process data a lot faster there. There was a particular data set we processed that took us roughly 2 weeks to process on our own cluster. We were able to process it in 2 days on Saguaro. But the problem was moving the data around. Once that data was processed, it took us almost a full 8 weeks to copy that data back from Saguaro to our own system. And that was just between competing systems on campus that were, almost in the same room. Whereas the data set took 2 weeks to process on our cluster, but when it was done, the data was there. There was no separate file copy stage. And just the sheer size of our data has been the challenge on that one. Trying to move to cloud or move things off premise, it actually dramatically slows down what we're able to do, unfortunately.
Interesting. So it's really networking limitation, and the offset with the processing speed just isn't sufficient to outweigh the networking costs. Okay.
Yeah, there's some types of data, like if you're doing genome research, for example, your data is very small, but your CPU cost is very high. In the case of our data, the data is all very large. And so that all that IO cost really adds up.
Yeah. So, relatively recently, there's a lot of talk about the concept of moving the tools data rather than moving the data to the tools. And this is just an extreme example of that.
Yeah, very much so. Having that processing cluster in our storage effectively in the same rack hooked to each other is something we just can't match anywhere else.
This mic is terrible. I also learned about, what was it, base 10 versus base 2 data sizing. Never heard about that before. So thanks for the info.
Yeah, absolutely. If you're at, for example, the Linux command line using tools like df and things like that, they're going to report your sizes to you in base 2. The sizes you see on marketing material are all going to be in base 10. And so, yeah, when you're at this scale, it's incredibly important to make sure you know what units you're looking at.
Are there any other questions for Nick today? I think that's it, Nick. I think we can wrap it up.
Great. Well, thank you, everybody. It was a pleasure talking today. And I believe Megan should be in the room. So if anyone wanted to walk next door and see that moon rock in the operations center, she would be happy to take you there.
Thanks, Nick. Have a good day.
You too.